This is the third section of chapter 2, and this is on the Maclaurin series. And basically what this is this is a series, actually an infinite sum, that will allow us to write particular expressions as this infinite sum of terms. So there are some examples here. So for example, this one here, so 1 over 1 minus x can be written as this infinite sum, and you can see the pattern, and that will go x to the 4 plus x to the 5. You can see what the pattern is up to x to the power n. Now you can get this actually from doing the binomial expansion. So if you did the binomial expansion of that expression, you would get that infinite sum. The same with the second one down here. Yeah, and again you can see the pattern, but can you see that what's happening is the signs in front are alternating between sort of positive, then negative, positive, negative. So if we were to carry on, this would be x to the 4 over, you can see it's going to be 32, and then the next one will be plus x to the 5 over 64, and so on. And then we'll be looking at in a moment how we can write the nth term, ensuring that we get the correct sign, how we can do these alternating signs like that. And the last one, you may have seen this already when you were studying e to the x, that actually can be written as that sum. And what the Maclaurin series allows you to do is to work these out from scratch. So you'll be able to work out why e to the x is this infinite sum, or why this is this infinite sum, and lots of other things as well. Now this is what Maclaurin's series looks like. Let's get a pen. So it's like this, and let's do it in black. So we have our function, and it can be written as the function evaluated at 0 plus the derivative of the function evaluated at 0, and that's the coefficient of x. Then the second derivative evaluated at 0. So what I mean is you substitute 0 in. That goes over 2 factorial. That will be the coefficient of x squared. Then the next one, the third derivative evaluated at 0 over 3 factorial. That will go in front of x cubed. Now if we wanted to write the nth term, in the book they use r, I'm going to use n. So let's think about this. So we're going to the nth derivative evaluated at 0. That will be over n factorial. Can you see that the derivative number is the same as the factorial, which is the same as the power? So then that'll be x to the power n. Now I'm going to do plus dot dot dot, because this is just the nth term. This is an infinite sum, so I'm not saying, right, that when we get to n it's the last term, it's just the nth term. It's an infinite sum. So that's the pattern. This is Maclaurin series. So it does mean we're going to be doing a lot of differentiation, a lot of evaluating at 0, but that does come with some limits, some rules which we must adhere by to enable us to write a function using this Maclaurin series. The first thing is that you need to be able to differentiate a function an infinite number of times. Okay, so the function must be able to be differentiated an infinite number of times, because it's an infinite series, and you can see that, you know, every term we're differentiating again. The second thing is that if we work out any derivative, or when we sort of differentiate multiple times and we substitute 0 in, we need to make sure that we don't get an infinite value, so we can't divide by 0. So in other words, any of the nth derivative, that could be the first, second, third, fourth, whatever, evaluated of 0 cannot be infinite. So it needs to be finite, basically. So you can't end up working out, putting 0 into it, and you end up with like Matha or something on your calculator. The next thing is that some of the expansions are only valid for certain values. So some expansions, I'll just put not valid for all real numbers, and you can see that up here. So I can get rid of this, and you can see, for example, the first expansion we've got up there. You can see at the end it says that this one is only valid when the modulus of x is less than 1, so it's only valid between 1 and -1, not including 1 and -1. It's the same for this as well, whereas the one for e to the x is valid for all real numbers. So, but some expansions are not valid for all real numbers. And the other thing is that we'll be doing some expansions for things like sine, cos, or tan. X must be in radians. Okay, so for trig expansions, X must be in radians. So there's a few things we just need to remember when we are working these out. Okay, right, let's move on to some examples. Okay, given that f of x can be differentiated infinitely many times, which is what we want for the Maclaurin expansion, and that it has a valid expansion in the form of this f of x equals a of 0 plus a1x and so on, where these are all real constants. Okay, show that the expansion must be given by this expression down here. Right, you'll notice that this has f of 0, f dash of 0, f double dash of 0, and so on. Okay, what we're going to do then, we need to work out, well, what is f dash of x? We need to work that out, and then we need to work out what f dash of 0 is. We need to work out what f double dash of x is, and then work out what f double dash of 0 is. So we're going to have to differentiate our f of x. So we're going to start first of all with this first term, f of 0. Well, f of x is given. So f of x given. That's what's in the question. So we can straight away work out f of 0, which means substituting in 0 into this expression for x, and that just leaves a 0. So I'll write that down, a 0. Right, so we've got the first term. So I can see that these match up. F of 0 is a 0. Okay, let's move on to the next one. So we need to differentiate f of x, and we need to find f dash of x. So if you do that, the first term disappears. This just becomes a1, the next term. Then the next term, that becomes 2a2. So plus 2a2. The next term after that, this one here, will become 3a, 3x squared. I forgot the x here. 2a, 2x. So the next one will be 3a, 3x squared. Now the next one, that would be a4 to the power 4. So that becomes 4a, 4x cubed. So you can see the pattern like that. So now what we're going to do, we'll work out what f dash of 0 is. So we just put 0 into this expression here for x, and that just leaves us with a1. Okay, so a1. Now again, I can see that where I've got f dash of 0 here, I get that equals a1, so that matches up. Let's carry on the differentiation. So let's differentiate a second time. Maybe we'll do this three times, so we can see the pattern. So differentiating f dash of x, what we're going to get, well, the a1 disappears. We're left with 2a2 plus, that will be 6a3x plus 12a4x squared, and so on. So we'll work out f double dash of 0. So f double dash of 0 is going to be 2a2. 2a2. So what does that mean? That means that a2 is equal to f double dash of 0 over 2. That's the same as saying f double dash of 0 over 2 factorial. So let's just sort of highlight these things. So I've got a2 equals this. So going back to my original expression, a2 is the coefficient of x squared, which is the same as the coefficient of x squared here. Yeah, so we're showing that these things match up. So we'll now move on, and this will probably be the last one that we do. Differentiate a third time, so that the first term will just disappear. Then I'll end up with 6a3 plus 24a4x, and so on. Let's work out f triple dash of 0. So that will mean all I'm left with is 6a3. So that means that a3 equals f triple dash of 0 over 6, and 6 is 3 factorial. So we've said that a3 equals this, and a3, well, that's going to equal that next term there, which we haven't done, but following the pattern, that's got to be f triple dash of 0 over 3 factorial, which is what we've got. Now, what I need to do now is to show what happens when I differentiate r times, because that's what they use in the question. So, looking at the pattern, I'll have the rth time that I've differentiated with 0 put in it, and it will be the x to the power of r over r factorial, and this is for r equals 0, 1, 2. Yeah, it has to start from 0, because if we notice, the first term is just a number. There's no it's a coefficient of x to the power 0, isn't it, that one? So we're not starting from r equals 1, but r equals 0. Now all we need to do now is to come to our conclusion, which is f of x equals a0 plus a1x plus a2x squared plus ... can be written in the form f of x equals, bad bracket there, f of x equals f of 0 plus f dash of 0 x plus ... since, what did we say, a0, and we've shown it, a0 we said equals f of 0, yeah, that's here. So a0 equals f of 0. a1, what did a1 equal? Well, a1 was here. a1 equals f dash of 0. a2, what do we say a2 was? F double dash of 0 over 2 factorial. a3, we did that one. f triple dash of 0 over 3 factorial, and we'll just show that actually the pattern is the rth derivative of 0 over r factorial. I need to say that that will equal a subscript r. So basically it's the coefficients that we've worked out here. You'll notice that the powers of x squared, x cubed and so on, they're the same, x squared. We're just showing, right, okay, does that coefficient become this? Yes it does. Does this coefficient become this? Yes it does. Does this coefficient become this? That's what we've done, and we've proved it. Now because this is asking us to express log 1 plus x as an infinite series, then there's a couple of assumptions that we need to make. That actually that this can be differentiated an infinite number of times, differentiated infinitely, and also that f, the nth derivative of 0 is not infinite. Okay, that basically means that you don't divide by 0. Okay, so as the question's asking us to express it as that, so we can assume that those two things are true. Okay, so let's start with part A. So you'll remember, or if not, if you don't remember the Maclaurin expansion, let's write it over here. So f of x can be written as f of 0 plus f dash of 0x plus f double dash of 0 over 2 factorial x squared plus f triple dash of 0 over 3 factorial x cubed plus dot 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 up to the nth term, which is going to be nth derivative of 0 over n factorial xn, or you can use the letter r. Right, so that means we need to work out each derivative and its value at 0. So let's start with f of x, which is given in the question. So let's work out f of 0. That's going to be the log of 1 plus 0, which is the log of 1, which is 0. Next one, f dash of x. So that will be 1 over 1 plus x using the chain rule, f dash of x over f of x. And I'm going to write it like this because this is going to be useful for the next bit when I want to try and differentiate that again, because I don't really want to start using things like the quotient rule or things like that at this stage. Right, so I can now work out f dash of 0. So if I put 0 into that, I'll end up with 1 plus 0 to the power negative 1, which is just 1. F double dash of x, using how I've written it here in this form, that'll be more useful. Using the chain rule, I'm going to get negative 1 plus x to the power negative 2. F double dash of 0 then is going to be negative 1 plus 0 to the power negative 2, which is just going to be negative 1. Third derivative. So I'm going to have 1 plus x to the power negative 3. So you can probably see by this stage that it does look like this is going to be something that I can differentiate an infinite number of times, because all that's going to happen is you're going to be multiplying by this power, and that's just going to get more and more negative. Yeah, so there's not going to be a point where you get to something which you can't differentiate. So I know it satisfies those rules, and basically I'm never going to be dividing by 0 because I'm always going to be having 1 plus 0 in the denominator when I work it out, so I'm never going to have to divide by 0. So you can see from what we've got so far, it works with those rules. Okay, so let's do 2, 1 plus 0 to -3. So that will just give me 2. And I'm going to do one more. Just help me find a pattern. -6, 1 plus x to -4. So I've worked that out there. Let's just work out what that value is of 0. When you get lots of dashes, you can start putting numbers in, or you can even use Roman numerals. Otherwise it gets messy when you start putting loads and loads of dashes in. So that'll be -6, 1 plus 0 to the power -4. So that gives me -6. Right, so let's plug all of these values into the expansion. So I'm just going to highlight what are derivatives at 0, what they were, so that we can see that for the next bit. So f of x can be written as f of 0, which is 0, plus f dash of 0x, so plus 1x, plus f double dash of 0, so that's -1/2 factorial x squared, plus f triple dash of 0/3 factorial x cubed, plus -6/4 factorial x to the power 4 plus ... Let's tidy this up, because what I'd like to be able to do is to write down what the nth term is. So x, so the first term is just 0, so it's x. Now the second fraction becomes -1/2, so -1/2 factorial. The next one is a positive, and 2/3 factorial is 2/6, which is a third. The next term after that is -6/4 factorial, which is 24, which is -1/4. And because we've done 4 terms, I can see the pattern, which is going to help me to work out the nth term. So let's first of all deal with the alternating signs of positives and negatives. And the way that I can do that is to do -1 to a power. But you may already know, and I'm sure you already know, that if you do -1 to an even power, you'll get a positive. If you do -1 to an odd power, you'll get a negative. Now, if we call the power n, so for example, if I put n here, then every time I get to an even power here, I'm going to use n for this power, I'd end up with a positive. And I don't want a positive, I want a negative. And every time I have an odd power, like here and here, I would end up with a negative. I don't want that, I want the opposite. So to get that to work, what we need to do is add 1 to the power, or we could take 1 away from the power. Now what that does is it makes the power correct so that you get the right sign. Otherwise the signs will alternate, yes, but they'll alternate the wrong way. So that's one way in which we can get the powers to alternate the way that we want them to alternate. Right, so that's that bit dealt with. Then you can see that the next bit here, it's a fraction, and that fraction is going to be 1/n, and it's going to be x to the n. Okay, now you could, if you want, put this here on the top of this fraction instead, but I've just sort of laid it out in a similar way that we've got this written. So this will give us the nth term. So this thing of adding or subtracting 1 from a pair is useful when your powers alternate, but opposite to the way you want, they would normally do according to odd and even powers. So let's just stick a box around this here, because this is what we're going to use for the next bit. So basically this is the expansion of natural log 1 plus x. Here it can be written like that. Okay, part B. Using the first 3 terms of the series in part A, find estimates for log of 1.05 and so on. So first 3 terms. So we're only interested in 1, 2, 3. We're not going to go any further, so we're only going to use those to help us. Now, because we've done the expansion of log of 1 plus x, we don't make x in the first bit. We don't make x 1.05 because we've already got 1 in a bracket. We make x what we need to add to 1 to get 1.05. So x is going to be 0.5. Sorry, 0.05. That's what x will be. If we make x equal to that, put it into the expansion, which I'll do down here. So that'll be 0.05 minus half times 0.05 squared plus a third times 0.05 cubed. Okay, so let's do that on the calculator and see what we get. So 0.05 minus a half times 0.05 squared plus a third times 0.05 cubed, and how many decimal places do they want? It just says estimates. Okay, so let me just write down what I see on my screen. 0.04879 1, and then it seems to be like 6 recurring after that, so I'll stop there. Right, let's do the second bit. So with the second bit, we would make x equal to 0.25. So same thing again, 0.25 minus half times 0.25 squared plus a third 0.25 cubed. Just did that on my calculator. Again, I'll write down what I see for display. 0.2239583, and then it seems like the 3 is recurring. And then the last one here, log of 1.8. So in this one, x is going to be 0.8. And so it's going to be 0.8 plus half 0.8 squared plus a third 0.8 cubed. So let's just correct that plus there. That should be a minus. And that gives me, I think I've just got about enough space to write down as much as I can. So 0.6506, and again it looks like the 6 is recurring because I've got loads of 6's and then a 7 there at the end. Right, and then it says comment on the accuracy of these results. So let's actually work out what the exact answers are and how good our estimates are. So if I work out the natural log of 1.05, I get 0.47901. So for the first 1, 2, 3, 4, 5 decimal places, it's correct. So this part of the expansion, if you rounded it to 5 decimal places, is correct. So I'd say correct to 5 dp here. Next one, so let's work out the log and an actual log of 1.25, 0.223. Now, if I rounded it, this would only be correct to 2 decimal places, because 3 decimal places, this would round to 0.224, and I've actually got 0.2231. So actually, this is only correct rounded to 2 decimal places, although they both go 223. We're talking about rounding. Okay, so correct to 2 dp. And the last one, let's work out the log of 1.8. Okay, that's not correct at all. My calculator displays says 0.5877. So, you know, this isn't correct to any number of decimal places. Probably only correct actually to 1 decimal place, because what I've got my calculator would round to 0.6. So let's just put that, and we'll just put correct to 1 dp. Now this should show you something, that the closer that x is, or the closer to what's in the bracket to 1, so the closer to 1 this is, or -1, sorry, the closer to 1 this is, the better our estimate. Here x was small, here x was a bit bigger, here x was bigger still. So the smaller the value of x, the better our estimate with a small number of terms. I'm guessing if I use more terms, I would get more accuracy. Yeah, but you know, that's not bad. You know, work this out from scratch. You know, if you didn't have a calculator, you know, you could use the expansion and work out like log to some fairly significant good levels of accuracy. Right, now because the Maclaurin expansion is an infinite expansion, you will often be told how many terms you need to write down. In this case it's 4 terms, and we are writing the expansion of sine. So we're assuming that sine can be differentiated an infinite number of times, and when we work out the value of those derivatives at 0, the value is not infinite. So let's just write down our expansion up here to remind ourselves. So f of 0 plus f dash of 0x plus f double dash of 0, I was going to write x down, over 2 factorial x squared plus ... So we can work out the rest. So the first 4 terms, so f of x, our function, is sine x. So we'll need to work out what f of 0 is. That's sine 0, and sine 0 is 0. Our first derivative, when you differentiate sine, you get cos x. So the value of our derivative at 0 is the value of cos x, or cos 0, and cos 0 is 1. Now we are dealing in radians, so remember that's one of the conditions for this expansion. For a trig function, it's in radians. Now we're working out sine 0, cos 0. That doesn't make any difference. Radians or degrees, 0 radians is 0 degrees, so that doesn't make any difference in this particular case, but just be aware of that. Next one, second derivative. So if you differentiate cos, you get negative sine. So the second derivative of 0 is going to be negative sine 0, which is basically negative 0, which is 0. Next one, when you differentiate negative sine, you get negative cos. So the value at 0 is going to be negative cos 0, which is going to be negative 1. Now we only need the first 4 terms, so we don't need to go any further than that, because this one here is going to be the 4th term, so we don't need to go any further. We don't need to know what the nth term is, but we may write the nth term down just for, you know, it's just so we got it there, so you know what it looks like. Okay, so let's write down the expansion over here. So sine x, f of 0 is 0. Then we're going to have 1x. This will be tied up in a minute. Then the next term is going to be plus 0 over 2 factorial x squared. The next term is going to be negative 1 over 3 factorial x cubed plus dot dot dot. Let's tidy that up. So we have sine x equals x minus 1 over 3 factorial x cubed. Now if we have a think about this, if I were to work out the 4th derivative, so let's put f4 there. It's not f to the power 4, but the 4th derivative, I would end up, if I differentiate negative cos, I end up with sine x. Now what will happen is I've basically gone back to here, and I would end up going around that loop again and generate the value 0, 1, 0, negative 1 again. So the next term, x to the power 4, will disappear because I'll have 0 over 4 factorial. The next term will reappear as a positive because I will have differentiated again and ended up with working out cos 0, which is 1. So the next term that appears after this will be plus 1 over 5 factorial x to the 5. Now we can see the pattern. I reckon the next one's going to be negative 1 over 7 factorial x to the 7, and so on. Now let's see if we can work out what the nth term is down here. So it's going to be 1 over an odd number. So if I started with n equals 1, then 2n minus 1 will give me the first odd number. Okay, so here I'm going for n equals 1, 2, 3. So I'm not starting at 0, I'm starting at 1. So this is going to be for n equals 1, what I'm writing down here. The power of x needs to be the same, so it's going to be x to the power of 2n minus 1 here as well. And then we need to deal with these alternating signs, and that's these here. So the first one is positive, negative, positive, negative, and so on. Right, so let's work this out so that we don't get it wrong. So the first thing is the first term, and the first term we get when n equals 1, that works out as a positive 1. The second term will be generated when n equals 2, because you do 2 times 2 minus 1, which is 3, so you'll get the 3 factorial on the power 3. I get a negative in terms of the sign that's in front. The third term, I will get that when n is 3. You do 2 times 3 minus 1, so you'll get the power 5. Let's sort that 3 out. That is positive. Right, so what does that tell me? That tells me that when n is odd, I want it to be positive. So when n is odd, I basically want a positive sign in front, and when n is even, I want a negative sign in front. So my term here, this nth term, I'll write it over here, probably not the best place, but I haven't got space. will be -1. Now let's think about this. If I just put n there, like this, I won't get the right sign, because when n is odd, I'll get negative, and when n is even, I'll get positive. So I'm going to put +1. So I could either do +1 or -1. So I'm going to put n +1 here for my nth term. I suppose I should put a plus there. Right, so we're going to be using this expansion that we've just worked out, the first 4 terms. So this is what we're going to use, our tidied up form, 1, 2, 3, 4 terms to work out. Actually, we're only going to be using the first 2 terms of that 4-term expansion. So we're only going to be using that bit of it there to do part B. And in part B, it just says use the first 2 times to find an approximation for sine 10. So sine 10, remember we need to be in radians, so we don't make x equal to 10, that will be a mistake. We change 10 degrees into radians, so just remember that 180 degrees is pi radians. So if you want to get to 10 degrees, you need to divide by 18. So sine of pi over 18 is the same degree, same angle, but in radians. So the sine of pi over 18 radians, we plug into the expansion, which would be pi over 18 minus 1 over 3 factorial pi over 18 cubed. Now I want you to notice something before we work it out. This bit here is a bit like the small angle approximation, isn't it? When the angle is in radians, if this is small enough, if the angle is small enough, then basically this approximates the sine of that angle. Now, why would that happen? Well, if this angle here is in small in radians, then what will happen is if you're cubing a small number, it gets even smaller. All of these terms here, this one, and this one, they're going to be too small to even bother about, because they're just going to be very, very small. You're multiplying by a very small number. So that's why that small angle approximation works, and you can see it here in this Maclaurin expansion here, or series here. Right, let's stop the waffle and work this out. I've done that on my calculator, and I'll get 0.173646829. Now the question doesn't say anything about how much we need to round to, so I could leave it like that. I could, if I wanted to, change it to 3 significant figures. Now because we're doing an approximation, really I shouldn't be using an equal sign. So let's say that it's approximately that. The more terms in the expansion I use, the better my answer would be. So let me just write this down to 3 significant figures. So that would be 0.174. That's 3 significant figures. Now I'm actually going to work out what the sine of pi over 18 actually is and compare it to my answer. The question doesn't ask me to do it, but I'm just interested to see. So making sure my calculator is now in radians. It didn't need to be in radians for the last bit because I wasn't working the sine, cos or tan of anything out. So let me now do the sine of pi over 18 and see what happens. Is this expansion any good? Or shall I just use my calculator? Right, this is interesting. So on my calculator, I get the exact value as 0.173648177. Now I only used 2 terms of the expansion, and I can see that my answer is correct now. 4 decimal places it's correct to if I round it. 5 decimal places, it's correct to 5 decimal places. Look at that. They were both round to the same thing, to 5 decimal places. So only using 2 terms, I've got quite a bit of accuracy. Now, if it was a bigger angle, that accuracy might not be as good. Okay, so there's the Maclaurin expansion there. I've used N throughout, they've used R, it's the same thing. And you now do exercise 2C on pages 43 to 44.